information we gathered during the PASSME project. PASSME project was a project. Hey, I try to get to the next slide. Okay, the PASSME project is the PASSME is called Personalized Airport Systems for Seamless Mobility and Experience. So that means we have to go faster and fast airports and do it stress-free. And there are 4 breakthroughs in this project. One on passenger demand forecast systems. That means that you can predict how many people will come there. So if you, for instance, have the number of people working at the customs, they can decide how many people they will have there to have as less rows as possible. The luggage flow management is breakthrough number 2. For instance, luggage can be picked up from your house and brought to the hotel, and then you don't have luggage at your travel, only hand luggage, and that will of course speed up your flight. And then the redesign of passenger-centric airport and aircraft interiors. We changed aircraft and airport interiors. One of them will be shown here. And then the other one is the personalized device and smartphone application, so that you get, during your travel, you get information on your personalized device and smartphone application. So, but now the focus is on breakthrough 3. And today we have 3 presentations. One of 10 minutes on improvements for faster boarding. That's by me, Peter Vink. Then we have in 10 minutes the design of the new PASSME seat by Andrè Castro from Almadesign. And then we have the mechanism in the new PASSME seat, and that's done by Antonello Nardini from Optimares. And then we have time for questions, and then you can put the questions with the chat, or you can do it by microphone, but we come back to that later. And this will be facilitated by me. Part 1, scientific improvements for faster boarding. If you look at the whole travel during a flight, you have a situation before flight, when your luggage stow in your airplane, then taxiing, taking off, after taking off, then during the cruise flight, until ending at the airport. And you see the comfort is lowest with luggage stowing. Also during cruise flight, it's significantly lower than the rest. But luggage stowing is really something which takes attention. This was recent research. About 10, 20 years ago, this was not a big issue as now. And this is based on a study in Bowens. So it's worthwhile to pay attention to that. So we're going to focus now on boarding. Boarding is important to speed up turnaround, and there are 2 types of turnaround defined by Kieskowski and Kizil. And the short one is in fact the turnaround where only passenger boarding and deboarding is, of course first deboarding and then boarding is done, and baggage unloading and loading. And on average this can take 23 minutes. Then there is the complete turnaround, the full turnaround, and it will take in a 737-800 45 minutes. And then the crew is replaced, servicing galley, servicing cabin, refueling, servicing toilet, servicing water. So much more activities are taken. But the passenger boarding, deboarding, if you influence that and make that shorter, the whole turnaround can be shorter. And this can be important in getting your next flight, because sometimes you have to catch up a slot, and if you lose your slot, well, you get a delay. We had all scientific papers which mentioned boarding in aircraft. We studied them, and there were 46 papers. Most of them were computer simulations, so they had a certain plan, and then they simulated if we change something, what is the effect. Six of them had real observations, and in those cases they observed how fast it was and how people experienced it. I will show an overview of the results in the next slides of these 46 papers. One outcome was, for instance, by Marelli, is one of the papers. He showed that 2 stairs reduced boarding time by 5 minutes. This was done in a Boeing 757, so it's a little bit more larger airplane than the current A320s and the 737-800s. But the estimation of experts is that it's about the same in those type of airplanes. So you can reduce 5 minutes, but instead of using 1 stair, 2 stairs, and it's of course not that strange because you get into the airplane by 2 ways, and there's less aisle blocking. Another interesting finding is that several papers show that block boarding is slower. That block boarding is like this. You first, like seen in this slide, you first let the people in the back of the plane board, then the area before that, then the area before that, and then the area before that. And this is not faster than random boarding because for instance, in block boarding, people have to put their hand luggage in the bins, and if they have to do that together in a small area, it will cost time instead of saving time. Pyramid boarding, or the Stefan approach, is faster, and that's the way, but it asks much more organizational effort from companies, because then you have to put first the people in the back of the plane next to the window, and then you do this area, and then you do this area, and finally you do the last area. Theoretically, this is much faster, but you have to assign people to places. There's another issue that sometimes people travel in groups, and of course you want to have the frequent flyer first, and this conflicts with this, and then on top of that you have to organize this as an airline. KLM did some experiments with that, and they found indeed that it could deliver 3 to 4 minutes more faster boarding, but the big issue was the organization of this. Another possibility to improve the boarding time is by preparing and training the passengers. Interestingly enough, when we tested 2 situations and we did the second time exactly the same, it was always faster. So when you train people, it can reduce boarding time. And one possibility is that you train people before getting into the airplane, and this was shown by one of our students, a movie by Peter Texkin. I will show you the main issues of the main elements of that movie. Another experiment we did is light guiding reduces boarding time by approximately 3 minutes. It was also done in a 737, and this movie maybe explains a little bit how it works. The last one should be red. It's now a little bit orange on the slide, but it should be red. And we did these experiments in this fuselage. Another experiment we did in this fuselage is we created a wider aisle from 16 inch to 32 inch, and it reduced also the boarding time by 4 to 5 minutes. And what we did here is an experiment, and we had an area, the green area, where the old situation was, and the the purple area where the wider aisle was there, and we measured. We gave people hand luggage. Everyone got one piece of hand luggage. What the effect was that there was always a hand luggage which didn't fit in the bins. And so we did the observation and we measured the time, and this is the way we found out that the wider aisle could improve the time. So it was 4 to 5 minutes faster. The experience, our impression that the experience was better, but that should be studied further. So the conclusion is the boarding time can be reduced by having 2 entries, the pyramid boarding, the light guiding, the preparation, and a wider aisle. I will now give the floor to Andrè Castro from Almadesign. He continues with the wider aisle, and he developed a new PASSME seats. So I will give the word now to Andrè Castro.
Thank you, Peter. I would also ask me if she could, share my screen. Thank you, Mead. Okay, so I think you can manage to see my screen now. So thank you so much, Peter. Wonderful presentation. So we are very lucky to be in this PASSME group with all these interesting people from a lot of different companies. And what we did in these years of study with PASSME was to try to develop this solution. And just as Peter said, we looked at different boarding strategies from the beginning of the project. And actually, yes, we concluded that a possibility would be to try to check at the different phases of flight, so boarding, deboarding, but also at what you do, so the luggage storage and the seating, and try to check if the aisle interference or the aisle blocking, as we can also call it, or the seat row interference will be one of the most important issues to tackle. And they are actually, because we all know that when we enter the aircraft, most of the times the passenger in front of us will have to store luggage in the bins, and this could take 30 seconds, but this could also take 2 minutes. And this is what we call the aisle interference or the aisle blocking. And there's also the seat row interference, which means that if you are sitting, for instance, next to the window and there's already a passenger sitting near the aisle, you'll have to ask him to stand up, and then you'll get into the line and you will sit near the window. But of course, this will also take about 30 seconds or something. So you lose time in these different, let's say, sequences. And when we look at this, we try to figure out different solutions for this. So we could maybe look at the layout of the passenger arrangement inside the aircraft, so the LOPA, and we could use other layouts, but this is quite difficult because airlines mostly use this standard layout on this one aisle aircraft, so it's 3+3. And basically what they change is the pitch and the seat manufacturer, but this is a solution which was not to change, let's say. So we also looked at improving seat number and things like this, but actually we looked at things like a sliding seat pan or a flip-up seat pan that actually improve the seat row interference. So it would be easier for us to get into the seat if we want to get to the window seat. But we also understood that the aisle interference was maybe the biggest challenge, and was probably there that we had to devise some kind of seat that could improve the aisle width. And so what we did actually was try to prevent the aisle interference, and for this we tried to develop, let's say, an adjustable width seat. This was our big challenge. And so how can we prevent this? So we thought, okay, the ideal scenario would be that when you board, you would have more space. So we could have an adjustable width seat, and then we would have a wider aisle, and this would solve most of the problems with aisle blocking, because then if you have a passenger which is carrying his luggage and which is storing it in the bin, you can just pass him and go to your seat and not have to wait. And we thought, okay, is this possible? So how can we design this? And we thought, okay, let's try to look at the seat. Let's try to look at the space we have in the seat. And maybe if we just have this different scenario when we board and deboard, and then we can have a standard seat for taxi, takeoff, and for cruise, then people will have a slightly, let's say, smaller seat when they are boarding, but after 5 or 10 minutes, then they will have a standard comfort seat, and the aisle is not so much wide, but then you are cruising, and then when you deboard, you again get a lot of space to deboard much faster. And so this is what we pursued, and so we thought, okay, how can we design this adjustable width seat? So we tried different concepts, and together, of course, with Optimares, who is a specialist and the manufacturer of seats. And we thought, after a lot of concepts, we decided for this one that you can see, which also carries at the back some purple lines, which are like elastic bands, that we thought, okay, if the seat changes, so it will stretch and it will compress. So let's have a metaphor of this. Let's devise some way that you could actually see this happening, which could be fun and could be something interesting also for the passengers. And so this is basically what we did. We developed the 3D models of the seat. We tried always to get the maximum amounts of space for the passenger, but also trying to fill in the gaps between the armrests and the back seat in order to try and squeeze the seat. And actually what we could do is we could, on the standards, let's say, one aisle aircraft, so an aircraft like a 737 or an 320, we could actually increase the aisle width by 16 inches, which is quite remarkable because it's almost double of what you have. And we could actually do this, and when you would board, you would use this wider aisle, so you could, as you see in the figure, just pass the passenger that is storing the luggage in the bin. And then when you sit, the you have a thinner aisle, a standard aisle, let's say, and the aircraft seat is again the same width as a normal seat, so you are quite comfortable. And then when you have to deboard, it gets back to the squeeze, let's say, position. And so for deboarding, the seats go back to the first position, and you can deboard using a wider aisle. So we thought this would be quite a promising concept. And actually, this is more or less the way it looks. Antonello will then actually explain this in detail. But we have a slight higher seat pan when the seat is in the squeezed position, and then when it opens, the seat pan goes down, so you have a very comfortable position in terms of ergonomics. And here is where the aisle is on a standard width. And like this, we thought, as Peter showed, let's first try this with simple mock-ups at TU Delft lab testing, the 737 they have at the university. And as you can see through the graphics there, actually with a standard width and with a PASSME aisle width, we can shave off about 30% of the time. In this case, with the test, we had something like 8 minutes of boarding time, but on average, the boarding time is actually more towards 20, 22 minutes. So if we can take 30% off of this, it would be actually fantastic. We tried it out at the test lab, as Peter showed, with the younger passengers and also with the elderly. And with the elderly, even the experience and the time reduction was a bit better. So this was also important, because with a wider aisle, we can actually just fit a standard wheelchair, and this could be a great improvement for also passengers with reduced mobility. So we also did a microscopic simulation with DLR, one of the partners of PASSME, and also here we used a scenario of let's say, low-cost carrier with the Boeing 737, and we used random boarding with 2 doors, and with a baseline scenario of about 10 or 11 minutes, we could also, which is actually shorter than it is, but we could actually also shave off about 30%. So we run about 150 simulation runs with the computer, and this also was a confirmation that the concept could actually work. And of course, we were happy with this. And so just as let's say, summing up what we were able to do is that for passengers, we think we can reduce the unwanted time with this. We can also probably, we didn't study the comfort, but we could also probably give more comfort to the passengers, because you don't have that standing and waiting for the passenger to store his luggage. And so probably we can improve the experience. For the passengers with reduced mobility, we could also improve the experience and also reduce the stress, because using your own wheelchair could be a great improvement for them. As for the airline, when we have less boarding time, you can, in some cases, probably not miss your slot. And with the passengers having better comfort in boarding, they'll probably use the airline again. So you could have some benefits of brand loyalty here. And finally, for the airport itself, when you have this more predictability, let's say, probably more robust operation, because of also the shorter turnaround times for the aircraft. Of course, we are basically talking about aircraft with one aisle, and so not very big aircraft there. We didn't study if the improvements would be so much, so we think this would be the, let's say, ideal scenario. And so for explaining in detail how the seat concept works, I will now pitch the microphone to Antonello Nardini from Optimares, and he will go on explaining exactly how the seat works.
Thank you, Andrè. Thank you. Let me share my screen. Okay. Good afternoon. My name is Antonello Nardini. I'm technical director of Optimares company. Optimares works for the PASSME project, has been focused on the development and production of the seat Andrè talked about. First of all, we have to say that the innovative boarding idea, the wider aisle, based on the enlargement of the aisle width, works only in a particular condition, only if passengers could sit down properly when the aisle is enlarged. For this reason, the development of the seat has been focused on one main concept: to find a way to compress the seat, leaving the passenger the possibility to sit down. If passenger cannot sit down when the seat is compressed, they remain standing in the middle of the aisle, dilating the benefit to have a larger aisle. The new seat had to comply not only with the main concept, this main requirement, but even with other market requirements. Since the beginning, we identified 5 challenges, and we worked to win them, all of them. 1, the seat must be utilized even in compressed configuration. The mechanism could be activated by passengers themselves. The mechanism must work even if not all seat places are occupied. The mechanism should not increase the complexity and the cost of the seat. And then the mechanism could increase the seat weight of maximum 5%. The first challenge, the seat must be utilized even in compressed configuration, has been won, forcing the main structure, and so the seat pans, to not overlap each other. Because if there is an overlap of the seat pans, this will not allow the passenger to sit down. When the aisle is enlarged, the seat pans are just compressed, So the distance between the armrest pass from 17.5 inches of the standard configuration to 14.8 inches of compressed configuration. In this way, the envelope, the total dimension of the seat pass from 59.5 inches to 51.5 inches. And the increment in aisle width is of 8 inches per side. So a total increment, we will have a total increment of 16 inches. Considering a standard aisle width in the economy class zone of 16 inch, we are increasing the aisle width of 100%. The second challenge, the seat mechanism could be activated by passengers themselves, has been won by inserting a mechanical button on the aisle side end bay. When the passengers come inside the aircraft, they find the seat locked in the compressed position, allowing all the passengers to sit down without tightening the aisle. Once the boarding is completed, the passengers could push the button on the end bay, and then the seat enlarge and automatically lock itself in TTOL and cruise configuration. The third challenge, the seat must work even if not all seat places are occupied, has been won, allowing the crew members to manually lower the unoccupied seat pans. The crew member could easily identify the unlocked seat thanks to the visual alert of the latch button. Then the crew member could lower manually the unoccupied seat place, allowing the seat to reach the taxi takeoff and landing and cruise latched configuration. The fourth challenge, the stretching mechanism should not increase the complexity and the cost of the seat, has been won not using electrical or electronics parts. In this way, the complexity and even the cost of the seat is not increased. The mechanism is mechanical and utilizes actuators similar to the ones currently used for the recline movement of the backrest in the standard seats. The fifth challenge, the compressing mechanism could not increase the weight over 5%, has been won utilizing the actuator of the backrest recline for the movement of the seat pans. In this way, yes, we maintain fixed at the backrest and designing properly the mechanism for the seat pan movement. In this way, we succeeded in maintaining the weight lower than 47 kilograms. That is 5% more than 45 kilograms that we have considered as a starting point, as a standard weight of a triple seat, economy class seat. Now we can go a little bit more in detail about the mechanism, how the mechanism works. The seat pans are connected to levers linked to movable cross member, able to slide on two guides fixed on the beams. These are the levers and these are the guides. And the cross member are moving on, sliding on these two mechanical levers, the two mechanical guides that are linked to the beams. Once the latch is disengaged, the weight of the passenger is able to make the seat pans go down, and so to move the cross member, enlarging the seat. When the mechanism is not latched and the passenger stand up, the actuators under the seat pan are able to pull the movable cross member and then to make the seat pan rise up, compressing all the seat. A key part of the mechanism is the latch. You can see the latch here on the end bay. It is a mechanical latch that acts directly on the sliding portion of the beams. This latch automatically fixes the mechanism when the seat is fully compressed or fully stretched. The latch is activated by the button on the aisle end bay. When the seat is not latched, is evident because the button is not flush. You can see in this little movie. And there is a red part highlighted when the button is not inserted and the seat is not latched. This is the seat, two pictures of the seat fully assembled that we presented at the Crystal Cabin, our final. And if somebody would like to see, to test, there will be soon 3 rows of this seat inside the fuselage in TU Delft. This is the last slide. One vision: reduce unwanted travel time, reduce stress, enhance travel experience. I remember we took this nice picture of all the team in TU Delft during the kickoff meeting. Thank you to everybody. Now I can pass the line to our moderator, Mr. Costello, Miss Costello.